If I said, hey, chapter 8 is about pipe flow, I am missing one important word. So start out by making sure we're clear about that. Regardless, it does pertain to pipe flow, and we're going to look at situations that are very typical out there in industry where maybe we have some sort of flow Q, and normally we express Q out in industry in things like gallons per minute volume flow rate. Um, and maybe we have some sort of length of pipe that we want to get through, and there's also a diameter that we need to specify or know, and a couple other things that would be relevant to the situation. What kind of flow do we get? Do we get laminar, transitional, or turbulent? What does the velocity profile look like? We'll get into that a little bit later on. What is the shear like? And of course, what is the pressure drop? So the pressure drop is very, very important, because when we size systems, one thing we want to do is we want to make sure that this fluid here has enough pressure to get through the pipe and exit with the way we want to. All right, so I started out by saying, hey, I'm missing something. So for starters, what I'd like you to do is think about what the pressure drop is. So pressure drop is essentially going to be P1 minus P2, or sometimes it's referred to as delta P in this case. So why don't you just go ahead and get started and work out P1 minus P2 in this case if we decide to use the Bernoulli relationship. So I'll get that up there. P1 plus 1/2 rho V squared plus rho GZ 1. Okay, that is the energy that the water has at the beginning, and you're going to set that to the energy of the water at the end and solve for P1 minus P2. So I'm going to go ahead and get going on that, and I encourage you to try to work that out yourself. Just go ahead and complete the Bernoulli equation and see, first of all, if you can get it right, and then also think about what I'm driving at there. So there's the complete Bernoulli equation. Unfortunately, I didn't quite get it in one line. And in addition, maybe one thing I should have noted, we're going to assume steady flow. And of course, that's very typical for this case. All right, so let's take a look at, obviously, the first thing we want to do with the Bernoulli equation, say, is there anything we can simplify? Well, if we assume this pipe is horizontal, and we'll do some vertical pipes, but for right now, we're going to start with horizontal flow, then the elevation terms, the elevation or the potential energy, gravitational potential energy goes away. Okay. How about the speed terms? We want to end up with P1 minus P2. Well, V1 would be the speed of the fluid here at the entrance, and V2 would be the speed of the fluid at the exit. Okay, the average speed. We note that the wall speed is, because of the no-slip condition, is less than the speed in the middle, but we're just talking about the overall average speed. And if it's steady, okay, and we have a constant pipe diameter, then the speed at the outlet and the speed at the inlet need to be the same. So we can get rid of those two. Okay, so if we go through it then and just do a little bit of algebra, this equation now is saying P1 is equal to P2. Okay, or in other words, if we're thinking of what is P1 minus P2, or what is the delta P, our delta P is equal to 0. And so that may seem to contradict something that I've really been emphasizing as we're doing this work, is that we want to be able to figure out the pressure drop. The fluid's going to lose pressure, and we have to give it enough pressure. And yet, one of our fundamental equations for fluids is saying delta P equals 0. Well, hopefully, you've thought, why is that? What's going on? This Bernoulli equation assumes that viscosity is limited and has virtually no effect. And that's a pretty good assumption. But when we get down to this point where we're trying to design and make sure that we have the pressure that we need to get through a system, we can't make that assumption. So we're not going to use the Bernoulli equation in this form in this case. We have to analyze this a little bit differently using viscosity. And let's go ahead and get going on that. We can get at it by asking this question. So if there's viscosity, why does viscosity lead to a pressure drop in this scenario? And that's pretty easy to get at. So first of all, just remind you, regardless of how we think of this situation, what we think about is going on at the wall. And we think of no slip at the wall. So that fluid is stationary at the wall. Laminar, transitional, turbulent, this fluid right here that's above is moving relative to that fluid there. So we have movement relative to another fluid. In addition, viscosity means there's cohesion. Viscosity is essentially a cohesive force between these two. And as a result, as if I just took and drew this slightly differently, if I thought of that layer near the wall as a rectangle and that layer above it as a different rectangle, as this rectangle slides that way below above the wall rectangle, there is going to be a shear force, okay? So if I redraw this one right here, it's moving to the right, and there's a shear back to the left because of viscosity. All right, so that's the why question. And then what we want to do is actually be able to quantify that shear and think about how it relates to delta P. So the first thing to do is to think about force and shear. And to do that, what I encourage you to do is at least visualize or try to imagine that as this fluid goes through, we're going to draw a cylinder for the entire fluid that's in there. So even if this pipe is really, really long, you can think of there being a cylinder of fluid in there that is going to be moving through. So I got this fluid cylinder in there, and it's moving like that. Okay, so I just drew earlier that this cylinder that's moving, there is shear backwards at this point, the top, and the shear backwards at the bottom. But recall, this is a circular situation, so there is going to be shear everywhere. There's going to be a shear like that, like that, like that, like that. Some sort of shear value. And I'm thinking that, these shear arrows go around the cylinder of fluid that's moving that way. And so they're the same value everywhere. There's the same value area because it's the same fluid interacting with the same wall. This in some cases, well, in our textbook, they're going to designate that as tau sub W for the shear at the wall. All right, and actually that's something that we want to be able to calculate. All right, well, if you think about that, if you think about steady flow, we're thinking of this cylinder as moving along at a constant speed, 10 feet per second, 16 feet per second, etc. What does that mean its acceleration is? It's 0. So if its acceleration is 0, the net force on that fluid needs to be 0. So what's going to balance that? What's going to balance that net? What's going to balance that shear force backwards? And it turns out it's going to be a difference in pressure. There is more pressure here than there. And so I'm going to draw a P1 that's large and a P2 that's not quite as large. Okay, and the pressure leads to a net force to the right, which exactly counters the shear to the left. All right, so we can explain why there is pressure drop in terms of force. There needs to be pressure drop in order to counter wall shear and therefore push the fluid along. All right, second thing, way of thinking about it also is we can explain the existence of a delta P by using energy, okay? That shear force is like friction. Friction takes away energy, and this pressure here puts in an additional energy like it does work. So we have shear taking away energy. Sometimes that's called viscous dissipation, and pressure putting the corresponding energy in. And for that reason as well, there needs to be a delta P. Okay, so the first thing to do basically is to relate this delta P to the shear. That ends up being an easy and useful relationship. So let's go ahead and get working on that. What we're basically going to do is taking a look at this red thing, which represents the fluid inside the pipe. We're going to say that the force to the right is equal to the force to the left. And why is that true again? We got steady flow. Okay, what causes the force to the right? Okay, well, one way of expressing that force to the right is just there is a difference in pressure, and that net difference creates a push to the right. So we could say that there's P1 times the area over here to the right, but we can get to where we want to be by saying there's a difference in pressure that's causing the force to the right. So being a little bit meticulous in writing out, I could say P1 times the area of the water at the inlet, or probably I shouldn't say water, it's fluid, minus P2 times the area at the outlet, okay, is the net force to the right. So that's pretty good, but what we would like to do is express it slightly differently. We like to use delta P in this case, so that would be, I could factor out the A and do P1 minus P2. Okay, so delta P Okay, how about this area? Well, we're doing, in this case, pipes with constant diameter. And that, of course, is the most common case out there. In addition, it turns out that we like to express this in terms of diameter. So this area is pi d squared over 4. Okay, what did we say the force to the left was? The force to the left was shear, okay? And reminding what shear is a lot of times expressed in things like pounds per inches squared. So I'll put that up there, and that's not bad. This is not a number we're going to use. I'm just discussing it. But I'd like us to be able to put in words what that means, okay? That means that there's 5 pounds of shearing force per every inch squared of wall area. Okay, so shear is also a force per area, but it is a shearing force per wall area. So over here, the force to the left is going to be the shear, which we're symbolizing as TW, okay, the wall shear, times the area of the wall. So I'm just going to put that up there and erase it. And I encourage you to see if you can pause the video and get through this, where we're going to solve for delta P in this case. But we don't want that area there. So hopefully, maybe you got it yourself, but otherwise, hey, what is this area of this wall that this shear ends up acting on? What is the area of that wall? Well, it is the exterior of a cylinder, and the perimeter here is pi d, and the length is L, so it's going to be pi dl. And I'm sorry, I didn't have an L in this diagram, but we're assuming that we're doing the same as that initial diagram that we had. Okay, that's a little bit messy, but that nonetheless is a good formula. We would like to simplify, so hopefully you can see the pi's go away and one of the d's goes away, and you could write a formula just like that. It turns out that your textbook, okay, makes it a formula for delta P, which it doesn't need to be that way, but if we solve that for delta P, we should get 4 tau W L over D. Okay, and that is a useful, good relationship. That is our first equation of today's lecture. Probably going to have 3 or 4 equations today that relate to this basic case where we have steady state flow in a pipe. Note, some equations for today are going to be for laminar flow. This applies for any flow. This applies for any sort of flow. It relates the pressure drop to the wall shear. We're going to work an example. So here it is. What is the wall shear in this case? Well, first of all, let's get oriented a little bit. Did the engineer who sized this pipe know what he or she is doing? They went with 3-inch pipe, and it's going to carry some sort of fluid flow for 100 feet. And the result is that in our system, if we have 20 psi at the inlet, we're going to have 16 psi at the outlet. So I didn't designate units, but assume that that's what those units are. Okay, well, first of all, that's a little bit too much pressure drop. Ordinarily, we would try to have less pressure drop than that, but nonetheless, it certainly could work. All right. Hey, what's the wall shear going to be? And you might feel like, wait a minute, what about viscosity? What about density, things like that? Well, it turns out this relationship, we can just jump in and work it without knowing those things. Let me get the relationship up there. And just remind you, you have it in your notes, so you could just go ahead and get going. Okay, there is that relationship. It can be solved for anything. So obviously what we want to do in this case is solve for the wall shear and be careful with our units. I recommend that you take D and L and make them in the same units, then it's just going to cancel out and be a pretty easy formula. And while you're working it, first of all, get the number right, and then I want you to look at that number and say, hey, does that make sense? Would a wall shear actually be that large? Let's see how that turns out. Well, if I was meeting with you guys, but I'm curious what you got. I got a very, very small wall shear, which turns out is pretty typical. So I did the algebra and solved for the wall shear. The delta P is 4 psi. I converted the diameter to a 1/4 foot, so it canceled with that length of 100 foot, and I got 0.0025. And then I was a little bit lazy. What about the units? Well, the units are going to be pounds per inch squared. There's nothing wrong about writing those units as PSI, but that pounds per inch squared helps me at least put in words of what's going on. That is 0.0025 pounds of backwards wall force per inch squared of wall. Okay, that's pretty typical. It'd be good to make sense of it. And if you go back to our starting idea on this all, our starting idea was we thought of any time there being a cylinder of fluid in there, okay, and there's a pressure force to the right, and that's exactly balanced by the wall shear to the left. Hey, so it might be helpful to get what that net pressure force is, and that would be the delta P that we have in this situation times the area. Okay, and you might want to pull your calculator out and do that calculation. How many pounds of force are on that fluid? So let's see, the delta P is 4, okay, and the area would be pi times the diameter over 4, diameter squared over 4. So pi times 3 squared divided by 4. Okay, and I'm getting 28.3 pounds to the right. 28.3 pounds to the right. Okay, how is that going to balance that? 0.0025. Remember, that is per inch squared of wall area, and this is a 100-foot pipe. We did a 100-foot pipe, so there is a lot of wall area in this case. And so for thin, long tubes, that's very, very typical that we get a very, very low wall shear. That means that if we're thinking, okay, do we need to brace this pipe because the water's going through there? Well, the shear is a force on the water backwards like that. So conversely, there'd be a force of the water on the pipe forward like that, okay? And it all adds up to about a 28-pound force, and that might be worth thinking about. But nonetheless, we get a very small shear. The second thing that's interesting to think about this shear is this shear is significant enough that it actually robs the water of some energy. All right, on to our next relationship for this type of situation. The previous result holds for all viscous flow in pipes, that shear equation that we developed. This next one does as well. So that is, hey, how are we going to choose our coordinate system for analyzing what's going on? And we certainly could use a typical Cartesian system where we have an X and Y plane. But hey, it's circular, so we're going to use rectangular coordinates. And that's going to be very useful as far as describing what's called the velocity profile. So what we're going to do is we're going to have our x-axis go right down the center of the pipe. Okay. And instead of having a y-axis, instead we'll have an r-axis. So we could imagine in this case, like here, r moving out here like this. And this point right here, if this were, say, like a 6-inch diameter pipe, this would be r is equal to plus 3 inches. And down here would be r is equal to plus 3 inches as well. And hopefully you remember how that all works with polar coordinates. If we were looking in towards the pipe that way, our r-axis would go out here like this. And any point, for any particular point, we end up thinking how r represents how far we are from the center line. So this point right here, let's say that that was 2 inches from the center line. And this point right here could conceivably have the same r. So we're going to have a x-axis, a r-axis, which goes out from the center line, and then we could have a theta axis, but it turns out that that's not that relevant. So let me erase a little bit and see if we can think about what's going on with that. Okay, probably the most important use of the coordinate axes is to describe the velocity profile. Okay, well, this fluid we're saying is for sure is moving to the right. So we're going to talk about there being a U, a flow to the right, a flow in the x direction, right? And we note that sometimes the flow is laminar, and that's in straight lines. Sometimes there's a little bit of up and down flow, and sometimes there's a lot of up and down flow, which is turbulent, but nonetheless move to the right. Okay, well, going back to laminar, that's going to be helpful for getting going. If we think about looking down at what the pipe flow looks like and what the velocities look like, we got to remember the non-stick condition, the no slip condition. So out at the exterior of the pipe, U is going to be equal to 0 because that fluid is just sticking there. Okay. Right. And At the center line, though, we talked about this before, if there's a certain amount of flow that enters the pipe and the flow out near the edge is slowed down because of viscous effects, the flow in the middle is going to be faster. So if we go to U at 0, we're going to get some sort of faster speed, which could be called U max, or in your textbook, it's sometimes called VC. So what's the velocity profile going to look like in this case? As a function of the radius. Remember, again, this axis or this axis right here is the radius. Okay, well, just a general description that we're going to get, kind of independent of whether it's laminar or turbulent. We're going to get slow at the edges, and we're going to get fast out in the middle. So basically what we would do if we were trying to draw it, we would imagine having our eye at some point here, and we're looking at the velocity and trying to figure out, looking at the fluid going by. Okay, if I did an axis that would look like this, where that's the x direction, okay, what we would see is up here, we would have 0 velocity out at the edge, and down here we would have 0 velocity at the edge. And in the middle, the fluid would actually, the fluid that's going past us right here, right there at that point, the fluid going past us would be going really fast. And then it would probably transition in between. So we would have 0 speed there, 0 speed there, fast in the middle. Okay, that is a good representation of what's going on with fluid speed. So I'm going to take away this x right here. In addition, I'm going to say that this is r right here, okay? And a little bit strange, but hopefully you get the idea that this is r down here like this. And this axis here, we could think about plotting u, okay? Well, what is traditionally done, and we did this earlier in the semester, is instead for the velocity profile, we just take these arrows, we just draw a vertical line to represent the point at which we're looking at the flow. So this vertical line would represent maybe this line right here, okay, in the fluid, right? And what we do is we take we take those velocities and we start them at that vertical line. So down here at the lower edge of the pipe, we'd have 0 velocity. Up here at the top, 0 velocity. In the middle, we would have VC, okay? And in between, we might have other velocities, okay? And usually, I only have 3 arrows there. Actually, strictly speaking, we have 5. Most textbooks I see that do a nice job, they maybe do 7. And sometimes they put a little bit of a line around there in order to indicate what's going on. All right, bottom line, we are going to have an x-axis in the case like this where it's a horizontal pipe, and we are going to have an r-axis, and u is largely going to be a function of r, and we want to try to get that velocity profile. Ideally, we'd figure out 6 different velocity profiles, but for this class, 2 is going to be enough. So what are the 6 different scenarios that we have? Well, last time we talked about there being laminar flow, transitional flow, or turbulent flow. And in addition, there's the question whether we're fully developed or are we at the entrance of the pipe. So for homework number 8, there are some great pictures in the book that give you a distinction between what happens at the entrance of the pipe and what happens once the profile fully develops. At the entrance of the pipe, we think of the flow as being uniform, and then those outer edges end up slowing down, and that middle ends up speeding up to compensate. If we had, say, 30 GPM going in, then and the outer edges are slowing down, the middle needs to speed up in order to maintain continuity. All right. We're going to do laminar and fully developed for right now and get these relationships. So previous relationships work for everything. This relationship works for fully developed. Although I must say that this equation here works for everything. The average speed of a fluid is the volumetric flow rate divided by the cross-sectional area. What's new for laminar? First of all, parabolic velocity distribution, fastest in the middle and rising to that peak in a parabolic fashion. That can be proven, and I'll have you glance through chapter 8 to see that proof. Secondly, the center line velocity is half the average. So if we get an average velocity of 10 feet per second, at the center it's going 20 feet per second. That can be proven as well. And finally, this equation for the velocity distribution can be proven as well, but we're just going to start working with it. So it says if I go to any r, okay, so I've got some sort of center line here where r is equal to 0. If I go out a little bit from there and I want to calculate the speed at r, there is my equation. So this could be like u at 1 inch is equal to the center line velocity times 1 minus 2r squared over the pipe diameter squared, where this r is not the radius of the pipe, but instead the radial position that we're interested in. All right, let's just see if it makes sense. Why don't you just go ahead and say, what if we're at the center line? What if r was equal to 0? What does this equation say u is 0 is equal to? Well, just think about it. You're going to go in and take 0 and put it in the correct place in this expression over here like this, and that would be in this r. So this whole term right here is 0. So I get this term in brackets at 0 is 1, probably 1 minus 0 is 1. And so I get the speed at the center line is equal to VC, and that's definition. Great. So you have these equations down. This is essentially our second equation of the day. You want to combine it with this equation here to get complete understanding. And let's do an example. Practicing this situation, pretty big pipe, 6-inch diameter. Sometimes that's a symbol for diameter. A lot of flow, 149.6 GPM. Okay. In addition, it's laminar and fully developed. All right. So let's do some calculations. What's the average speed of the fluid in that pipe? What is the center line speed? And let's go ahead and graph the profile. So a lot of this you ought to be able to get going on yourself. I'll be getting the equations up there and let's check in with each other and see how it went. All right, I got that this pipe was sized pretty large so that the flow is pretty slow. By the way, the fact that it's laminar, there's not enough information for you to figure it out. You need the nature of the fluid, the type of the fluid. So I'm just saying that the situation is such that it is laminar. Okay, I want to do Q over A to get the average speed, but I would like Q to be in more normal units. A good thing to remember is that a cubic foot is 7.48 gallons. So I took this 149 by 0.6 and I divided by 748 to get 20 cubic feet of fluid per minute is going through that pipe. And that's 1/3 of a cubic foot per second. So now I can get my average velocity, and I did Q divided by pi d squared over 4. The diameter I expressed in feet, so that was half a foot, and I got 1.7 feet per second. So there is the average velocity. What about the center line velocity? It's going to be twice that. I rounded off a little bit, but it turns out it's pretty close to 3.4 feet per second. So 3.4 feet per second. Okay. All right. So then the last thing to do is we want to graph the velocity profile. So once again, what we're doing is if this represents the pipe here, we're imagining a line going through that pipe. And what does the velocity look like at different points? So what is traditionally done in this case is we set up an axis that looks like this, where how far we're going out this way indicates how fast the speed is. And then many times we put the outer point here and here. And so this point right here at 3 inches would represent essentially the bottom of the pipe. And up here, this 3 inches would represent the top of the pipe. But both of those are R is equal to 3. So both of those are R equals 3 inches. All right, so we want to get that graph, and I'm going to work on it and try to get a couple of values to make sure that it has the shape it's supposed to have. So the first thing I did was I took that U equation and I plugged in specifics for our case. So this is the center line velocity, and then we want to do 2R over the diameter. And it doesn't matter what units actually we use for the diameter and the radius, is not as long as we're consistent. So I just decided to make life easier on myself. I'm going to make the diameter 6 inches, and then I'm going to plug in inch values for the radius. I'm going to try to evaluate this at a couple different points so I can put dots on there on that graph and see how it turns out. Encourage you to do the same. Okay, well, here's some results. So first thing I did was I said, okay, how about 3? How's that going to turn out? What if we are 3 inches from the center line? And it works out the way it should. If I put 3 into this expression over here, I get 6 in the numerator, and that all becomes 1. So I have 1 minus 1, and I have u is equal to 0 as my result there if it's equal to 3. So actually, that's not the first thing I did, but I'll get that up there. I'm going to put 0 speed right there like that. And this point down here, which represents the bottom of the pipe, is also 3 inches. So I should put a dot there like that. Okay, how about u equals 0? U at 0, which would be at the center line. Well, once again, you can see that that's going to be 3.4. So I'm going to get that dot. I'll get that point right there and there on this axis. So that represents 3.4. Okay, and then I got to do a couple others. I ended up doing u at 1. So I said, what if I'm 1 inch from the center line? And there's the math cracking through it. I got a little bit less than 3.4. I got 3. So if I go up 1 here like this, I'm going to be a little bit less than that. And also this point right here is also 1 inch. Sorry about that, that was blocked. This is also going to be a little bit less than that 3.4. Okay. How about if I go 2 inches from the center line? Well, there's the math down below, and I get hardly anything at all, which reflects the a parabolic type relationship. And of course, pardon me, that's about there like that. Okay, there like that. And so I get that nice parabolic relationship. What would be better in my mind, at least, I'm sorry, I've partially blocked, is that if we have velocity vectors to represent what the speed is like, and of course there'd be that velocity vector in the middle, which is hard to see because of the color pen I have. And so there is a picture of the velocity profile. And for homework 8, there's going to be lots of velocity profiles that you'll see that you'll get very used to what this looks like. Great, now we almost have it. So what our goal, one main goal with all this is to understand this scenario. What if you have a certain flow, got a certain pipe diameter, and maybe even a length of the pipe? What kind of pressure drop are we talking about? How do these different terms end up relating? And we can get there now that we have the distribution. So a lot of it's actually what we're going to do is we're basically going to go back to this equation here, that the pressure drop is 4 times the shear stress of the wall times the length divided by the diameter. And we're going to try to get that. But what we need is we need some sort of expression for the wall shear. And here's how we're going to get it. So first of all, just a reminder about shear. This case we're doing is laminar and fully developed. And please don't write down that shear formula down there. But what we did earlier, if you went back to like your notes from the first day, what I tried to do the first day is basically say like shear for a fluid is the viscosity times delta U over delta Y. Well, that was a very special case where we did not have a circular flow. Actually, we were a flow between 2 plates. Okay. Now instead, we are in circular flow. So we're going to take this delta U over delta Y and replace it with du dr. So first of all, that's the replacement in this case, that the shear is going to be the viscosity times du dr. Secondly, this equation only applies for laminar flow. So I was a little rough earlier in the year where I said, hey, this is the flow equation, tau equals mu times the rate of change of the fluid speed. That is a true equation for laminar flow for Newtonian fluids. All right, well, what we're going to do then, or you can see in the book, is the book then takes that U at R equation that we had a few minutes ago and says, well, look, I can take this and actually substitute it in there, because if I know U at R, I can come up with an equation for du dr, and I can put that in there. And that's easy enough to do. You'll see that in the book. By the way, what does du dr look like? Well, du dr is basically saying how is the velocity changing? And taking a look at our velocity profile over here, what we want to do is get the shear at the wall, because that's what's in this formula over here like this, the shear at the wall. So we're interested in how the velocity is changing at the wall. And up here, this dotted line represents the top wall, and down here, this represents the bottom of the wall of the pipe. And you can see that here, as we get near the wall, the velocity is really changing a lot. Whereas in the center, there's not much change. It's parabolic. And again, what's going on physically is we got the no-slip condition here, but that fluid's got to get through somehow. So this fluid over here is going to be going a lot faster than the fluid right there. So we get a substantial DUDR. Okay, the math I'll ask you to look at quickly, or suggest that you look at quickly in the book. Very nice work analytically, whoever figured this out. But you can see then that we could combine this tau equals mu DUDR for the wall and put that in there and see if we could crank through it. And with a little bit of neat math, including the idea that the center line velocity is twice the average velocity, here's the equation that they came up with. So go ahead and write this down. That's one of our main equations, in chapter 8. It's an equation for laminar, fully developed pipe flow. And the flow we get is going to be pi times the change in pressure, diameter to the fourth, over 128 times the fluid viscosity times the length of the pipe. And that holds for horizontal, viscous, laminar, fully developed flow. And let's apply it and see if we can get some numbers. First example where we'll use that Q equation. Let's see what kind of flow we get in a certain situation. So, by the way, we're going to, at the end, check that this is laminar. Let's just assume that it's laminar. So, we got a situation where we have some engine oil entering a pipe at 14 psi, that's gauge pressure, and we think that we can afford to have the pressure drop by 10 psi. So we're wondering what flow can we put through there with that pressure drop. Pipe's 10 feet long, it's 2 inches diameter. In addition, once we get that flow, and let's get that flow in GPM, we'll assess whether it's reasonable. We'll see what the maximum speed is, and we'll see what kind of wall shear we get in that case and work that out. So why don't you go ahead and get started. I made this easy so you can, this first one easy, so you can just jump in and use that Q equation. Well, I got a pretty high GPM, but it turns out actually that this pressure drop of 4 psi over 10 feet, that's a huge pressure drop. So there's a substantial pressure force there over that short distance. All right, well, taking a look at how it worked out, I used a little bit of a trick. Remember, there's d to the fourth over here. This is pounds per inch squared. So I could take this d to the fourth and do d squared times d squared. And I could enter this d here as 2 inches. And then this will be pounds per inch squared. And this will be inches squared. And those inches will cancel out. Other stuff's in feet. So I left the other 2 d's in my d to the fourth. Or I made the other 2 d's in my d to the fourth into feet. All right, I think before we get going on cranking the calculator, it would be good to make sure the units work out. So once again, this is pounds, and there's pounds there, so that's going away. The inches squared goes away, so that's going away. Let's see what else we've got. We definitely have a foot cubed here, and a foot there, and a foot there, and a second there, and a foot squared there up here. And if you can't crank through that, we're getting foot cubed per second, which is what we want, a volumetric flow rate. Okay, and on my calculator, when I went through it, rounding off a bit, I got 0.136 feet cubed per second, which doesn't sound like a lot, but again, that's per second. So to make it into GPM, I want to multiply by 60. And then each cubic foot contains 7.48 gallons. So that's going to crank out to, well, I got 61.2. Let me check that again really quickly. Yeah, 61.2 GPMs, which is an incredible flow for a 2-inch pipe. But once again, maybe we've got some sort of situation where we just need to get that oil through 10 feet and we're able to afford the pumping to get that kind of pressure drop. All right, that was our first question. Okay, how about the max speed? How about the max speed? Well, let's pause and think about that for just a second. Well, if you look through the equations you have, we don't have an equation that allows us to go directly from the volumetric flow rate to the max speed, but we can get the average speed, and that's what that calculation is. My calculator cranked out to about 6.2 feet per second. And so our max speed is going to be double that. So our answer for our maximum speed is 12.4 feet per second. So that engine oil is really, really moving. And once again, it's because we have a large pressure drop over a short distance. Okay, finally, how about the wall shear? Well, again, why don't you pause for a second and think about how you're going to get that. Well, that's not that hard. At this point, we only have a few equations, and we can take our earlier equation that related the pressure drop to the wall shear and rearrange it to solve for the wall shear. Wall shear could be in units of pounds of shearing force per inch squared of wall. So this is already in PSI. We already have that 4 PSI. If we can get our D in feet and our L in feet, they'll cancel out. So I'll get the numbers up there and we'll see if it matches what some of you guys got. Okay, so basically all I did was take the diameter and convert it into feet. And I ended up getting 4 PSI times 1/6 of a foot divided by 40. So let me try that myself. And my calculator is giving me 0.0167. And what are the units for that? It's pounds of shear per inch squared of wall area, pounds of shear per inch squared of wall area. And that may not seem like a lot, but hey, this is a pipe and we've got a significant amount of wall shear of wall area. That shear at the wall is enough to balance the pressure force. So there is our first example. All right, so second example. Let's say we get kind of greedy. We got the same thing. We got to push some SA30 oil through 10 feet. But instead of 60-ish GPM, we want to do 240 GPM. Well, clearly that's not going to work because we'd be trying to fit more oil through there. And so there is going to be a greater pressure drop as a consequence because, hey, there's going to be more rubbing. There's still going to be that no-slip condition, but that oil next to it needs to be going faster. So there's going to be a bigger velocity gradient. DU/DR is going to be greater. There's going to be more shear. There's no way this is going to work. So our job is to go and get the diameter. Hey, what are we going to do with the diameter? Well, clearly what's going to be, it's got to be bigger. And if it's 240, if the previous example was about 60 GPM and this is 240 GPM, intuition, a fairly decent intuition is going to be a lot bigger than 2 inches. Why don't you go ahead and pause the video? We're going to start with that same equation and see if we can manipulate it so we can solve it for the diameter. Once we're done, we're going to say, okay, in this case, what's the maximum speed? I'm sorry about that, pen's a little hard to read. And then finally, hey, let's confirm that it's laminar. The last example, we didn't confirm that it's laminar. Now maybe our assumption in using the Q equation for D is wrong because it might be turbulent. So we're going to work it out, assuming it's laminar, and then check it out at the end. First step, though, let's figure out what diameter we need. Well, if you want to look part way, one suggested approach is first we can solve it for D to the fourth. So there's the algebraic result. Before we get going, we might want to think about that problem with the fact that the pressure drop is in PSI. We're trying to keep the pressure drop at 4, making the pipe big enough. So this, thinking about some dimensions, this clearly we're going to make this into feet cubed per second. Easy enough. This is going to be in feet. So we've got feet and feet here, but we're going to have inches there. And I don't see anywhere else in this equation where there's going to be inches. So probably what we're going to have to do is take that 4 PSI, 4 pounds per inch squared, and convert it into pounds per foot squared, and then we'll be on our way. All right, I'm going to get the next line up there. Keep going and see if you can work out that diameter and get it in inches. All right, so here's the next step. If I've done it right, adjust the screen there a little bit, sorry. If I've done it right, unit-wise, everything should turn out to be in feet. So first, let's get rid of the pounds. Here's the unit for viscosity, pound second per foot squared, and then there's a pound down here, so those pounds go away. We'd like the seconds to go away as well, and I got that the volumetric flow rate was about 0.535 cubic feet per second, so the seconds go away. So we're just left with feet there, and if you take your time and look through all those units, we're trying to get the 4th power of the diameter and we end up getting feet to the fourth there. So I don't know if anyone got through that at this point, but if you crank through all this stuff and then do the fourth root, you get the diameter, okay, is about 0.235 feet. And if you convert that to inches, it's about a 2.8 inch pipe. Right. Okay, so that would be some good engineering work. We've got a scenario where we want to create a certain flow and we want to keep the pressure drop at some sort of upper limit like 4 psi, and that tells us what pipe size is going to do it. It does seem a little strange. Earlier we had 2 inch for 60 GPM, and now we're going up to 2.8 inches. But remember, this is just the diameter, and 2.8 inches has a lot more area for fluid to flow through than 2 inch. Okay, the area builds up because, you know, area is pi r squared, so it really builds up. So that actually makes some sense and does work out. Okay, well, there were 2 other things we were going to try to do. We're going to try to get the maximum speed, and now that should be old news. So to do that, we're going to start by getting the average speed, okay, by doing the flow, which we have, divided by the cross-sectional area, okay? And the flow, again, is that 0.5348 cubic feet per second. The area, we're going to take this diameter and make it into an area in feet. And you can check my work. When I got through there, I got an average speed of 12.4 feet per second, or 12.38 feet per second. And man, that is really some engine oil that's moving. In addition, we're going to figure out the center line speed, we're going to double that. So 24.4 feet per second. Good. Hey, one more thing. I should mention that this is maybe a little bit of a poorly posed problem. I said I got some engine oil entering here, and we're assuming laminar flow. This equation that we're using is for fully developed flow. There would be a transitional period at the beginning. I probably should have said that when the fluid enters this section of pipe, it's already traveled in some pipe and can be assumed to be fully developed at this point. Okay, one thing, how about that assumption that was laminar? If we're using this equation, it's laminar, we should check it out. So why don't you work on that and I'll work on it myself. So I was pretty skeptical about this one. That oil is really moving 12.38 feet per second. And so ordinarily that would lead us to think it's going to be turbulent flow or maybe transitional. But once again, we got this idea that oil's viscosity is high and its density is not that great. And so viscosity prevents turbulence. Putting in the numbers, I got the density, I've got the average speed. I took that diameter and converted it to feet and got the viscosity, the dynamic viscosity in the bottom. You can check that the units work out. I got 641, less than 2100, so that confirms that it is laminar. One more idea on laminar pipe flow, and that's a pretty good start for today. So laminar fully developed, by the way. So earlier we took that Q equation and we solved it for delta P, and that's very useful and helpful. It turns out that computation in general is headed a different way. And what people have done a lot of times for fluids is they've wanted to relate delta P to a variety of parameters, like the diameter, the length of the pipe, the Reynolds number, and finally, rho v squared over 2, which is, if you recall earlier from our discussion of fluids, we talked about there being a pressure energy, we talked about there being an elevation energy, and then a kinetic energy. So that's that kinetic energy term. Turns out in this case, it ends up getting expressed in PSI. So that'd be very nice if we could say, hey, the pressure energy, pardon me, the kinetic energy is so many PSI, what's the corresponding delta P? Well, what I'd like you to do to get warmed up on that is for this fluid here, let's get rho v squared over 2. Hey, someone might say, wait a minute, that's going to be hard to do because Professor Romani, your picture is not very good. This is laminar flow, so the flow out at the edge should be less and the flow in the middle should be more. And which V are we going to use? That is a very good question, but it turns out that we get good results by using the average speed there. So we're going to take that average speed, which was approximately 12.38 feet per second, and see if we can get what the corresponding PSI of that is. Okay, there's some number crunching without much thinking about units. I got the density, I've got the speed squared divided by 2. How is that going to turn out? Well, we've got slugs and feet, and if you remember, a slug foot per second squared is a pound, and it turns out that that is going to turn out to be pound per feet squared. And my calculator gave me 135.6. As I said earlier, it turns out we like to have pressure drop in PSI, so it would be good to have this term in PSI for something we're going to do in just a minute. So divide that by 144, and I've got that the kinetic energy is equivalent to 0.94 PSI. 0.942, I'll get that up there. All right, good. We'll hold that thought and I'll get what the next step is up for us to look. So this derivation took quite a bit of imagination on some engineers that were working on this stuff. But basically, there's our delta P equation. It's a good equation for laminar flow. Turns out that this next manipulation allows us to come up with a more general delta P. It's called a major loss equation that works for turbulent flow as well. So here's what we do. We're going to take this Q and replace it with this Q in this equation here and replace it with VAC. Then we're going to take the resulting equation and multiply it by 1, rho v squared over 2, rho v squared over 2. Why are we doing this? We want to have our delta P expressed in terms of rho v squared. Well, this rho v squared here is going to stay in the equation. That we did that multiplication entirely so we would get that. So I'm going to write it over here to the side. Okay. And if you're curious, you can pause the video and say, well, how is this rho v squared in the denominator going to work out with that pi d to the 4th, and then with that v pi d squared over 2, etc. But you can look in the book, and I'll get it up on the board. It turns out that we can rearrange all this other stuff so that we have an L over a D. Well, that's nice. That's unitless. Okay. And so this is PSI, or can be expressed in PSI. This is unitless. And then we can rearrange things so that we are left with a Reynolds number in the denominator, and in this case, a 64 in the numerator. All right, so that is the result. Wow, how is that useful? Well, it turns out, once again, we can think about pressure drop being caused by flow, speed or flow energy. Well, there's that term right there. We can think about it as being, depending on the length, the longer it is, the pipe is, the more the pressure drop. We can think about it as being inversely proportional to the diameter. As we make the diameter bigger, the pressure drop decreases. And then finally, we can think about it somehow being related to the Reynolds number. That's a little strange. But in any case, that is an equation you should box. What it turns out that as you get ready for test 2, this is going to be your governing equation. We're going to say the pressure drop in a pipe is proportional to the length and inversely proportional to the diameter. Okay, and then we're going to multiply it by the velocity pressure, v squared over 2. Okay, and then finally, we're going to put a coefficient in front, and that coefficient is called the friction factor. And that is really the main equation. This first equation here, that works for laminar flow. This is your basic equation for pipe pressure drop that you'll see on test 2, you'll see on the FE exam. If you go on the PE exam, you'll work that out. But then there's one more idea. Hey, for laminar flow, what is the friction factor? Well, the friction factor is equal to 64 over RE. And this F, again, is the friction factor. For laminar flow, it's 64 over RE. Friction factors are challenging to figure out. We'll get into that a little bit later on, maybe starting on that next lecture. Let's go ahead and calculate the friction factor for this particular problem. Let's get the number. So the friction factor would be 64. And we had a Reynolds number of about, I got 642 up there. So 64 divided by 642. Okay, I've got like 0.0996. If we were just being rough, in this case, we could say it's 0.1. Friction factors are usually small numbers. How about units? It's unitless. And hey, there's our first friction factor of the semester. Next lecture, we'll work out more on getting friction factors. That's a really good start on chapter 8, and hopefully you'll be getting an email from me soon saying homework number 8, which includes problems from chapter 8, is posted.